All right. Hi, I'm Brandon Dillon, and I'm the CEO at 2 Weeks, and we're a video game studio that's making games on the open web for you and your friends. And we wanted to start experimenting with showing more of our development and progress. And so I'm just going to hop on a live stream and start working on Vapor Solitaire, which is our pretty cool solitaire game. The thing that's on my list for today is to work on some optimization. So I'll show you some behind the scenes about how the engine works and just actually try to get some improvements in for it. But if you want to, I'll give you a quick tour of our development setup so you can get a sense for how all of this works. As you may be able to tell if you're a programmer, we code most of our games in Lua. So this is the main init script for Vapor Solitaire. In Visual Studio Code, which is a great open source integrated development environment. And we've written a custom plugin for our engine that allows us to edit and debug stuff in place. So I can just run Vapor Solitaire straight from here. This is running the native development version of our game. You can see that it just boots up as like a normal Windows application. But once we have the build in a good shape, we publish them to the web, cross-compiled using a technology called Emscripten. But Vapor Solitaire is meant to basically just be a very relaxing solitaire game. So actually, it seems like it got a pretty good draw. It has nice 3D cards and animations and that kind of thing. One of the challenges here is that because it's a 3D scene and not just drawing simple 2D images, the rendering stack is a little bit more complicated. And I want to try and get it optimized a little bit further, and I can show you how I started to look at this problem. So a great tool for debugging performance is called RenderDoc. And what this does is while you're playing a game, and you can actually launch regular applications too, like nothing's stopping you from running this on just arbitrary games that you have on your system. But what this does is it hooks all of the graphics calls that you make and then records them into a stream so that you can look at them step by step and see what they're doing. It's great for debugging rendering problems, and it's also great for looking at performance. So I have this already saved where it's set up so that I can run it with Vapor Solitaire. So if I just hit launch, it'll just run the executable. You'll see that it's capturing information about the game in the background here. Frames are very fast on this screen. But we'll hit play. It'll start dealing out the cards, and then we can just hit this F12 button to capture a frame. What we'll see is over here, now there's some frames captured. So if we just change some state here, like maybe it'll just capture a different frame in progress there. You can see I've got these different screenshots. But what's cool is I can open these up and get a detailed view of everything that happened that put that frame together. If we go back over here to the texture viewer, I wonder if I can flip this. There we go. This is what the final frame for the game looked like, but you can actually see all of the individual graphics calls that were made. So here's the call that's drawing the cool caustics that are sitting underneath of the screen. Here's a color overlay that's this texture like painted on the screen, so we get this nice kind of like gradient water effect on top of those caustics, and then it's starting to draw the individual cards. And so you'll notice actually, so like I'm stepping through these, there's a bunch of the backs of the cards, that kind of thing. I'm not actually exactly sure. So it doesn't look like anything's happening on the screen here, but it is actually. So what's going on with these is this is rendering cards, the back sides of cards. So like you can see these textures that are getting mapped in here. These are for cards that are rendered in the background. So this is a good example of something that's like if we could eliminate this from the render process, we could cut a bunch of draw calls, which would help performance a lot. But the biggest optimization that I want to make actually is you'll see that each of these cards here is getting rendered individually. There's 52 cards in the deck. That's 52 draw calls. It's actually double that because we're rendering the backs of the cards as well. What we would ideally be doing is doing instance rendering, where we render a bunch of the cards at once. The thing that you need in order to do instance rendering, though, is that you need all of these cards to be in a single texture. and then you can instance it so that you get different texture coordinates for each of them. So what we need to do actually is produce what's called an atlas of textures. And so like instead of having all of these cards split out into individual images, we'll make one big image that has a bunch of cards in it, and then as we're drawing things, we'll sample little subsets of it. I don't actually know if we'll be able to kind of get through a full implementation of instance rendering for the cards in the stream, but that's what we're going to be working on. And so the hope is that we can get this call reduced to just a handful of draws instead of the 52 plus that are in there now. You can see the draws coming in here for some of the UI elements as well. But I think we can get started on it. And to talk about the atlasing a little bit, this is actually a pretty common problem in graphics programming. And there's a great reference. I'll shout out Blackpawn, who's a excellent ex-demo scener graphics programmer. I had the privilege of working with him at ArenaNet back in the day. But he has this great blog that has this text section that includes a lot of just helpful programming insights. Most of these were written in kind of like the early 2000s, so they're quite old, but they're pretty comprehensive. A favorite, actually, if you needed to go figure out the math for point and triangle test from scratch, it's a great one here. But the one that has my favorite technique for building atlases is this packing light maps algorithm. And so light maps are when you it's a style of rendering where you bake lighting information into a big texture that then gets mapped onto the. And so you can do like very expensive ray tracing offline in a 3D tool and get nice lighting on the scene, and then basically copy all of that lighting into the texture and then render it really fast at runtime because you don't have to do the ray tracing anymore. But it has a similar problem to this, like, we want to render a bunch of cards at once, which is you don't want a bunch of, like, individual textures for every single surface that needs to receive lighting. You want to have a big texture that has all of them packed into one place. And so this is an explanation of an algorithm that basically, you hand it a bunch of images that you want to pack together, and then it has a sort of simple method for kind of partitioning space so that it can pack all of those into a single texture. Nice little algorithm here for it, and then you can see a final image with a bunch of stuff packed into one. This is roughly where we're hoping to go, right? Except, well, the cards will be bigger, but if we had a texture sheet that had a bunch of cards packed into it, we'd be on a great path. And actually, we have, for our UI module, we wrote a atlasing system. Let me actually see if we can see that in that profiler. Let's pull this back up. Are any of these packed into? Usually text is the thing. Yeah, here we go. So this is the draw call that's rendering this little new button. And if we go look at the texture that's inside of it, you'll see it's got this kind of interesting structure that you'll see play and new. Those are the only two words that actually show up as text in Vapor Solitaire, because it's just the play button in the beginning and then the new button afterwards. But this is actually laid out in an atlas using that technique above, and it's basically every time we needed a new letter, we have one big texture for all of the fonts that we're using in the game. And it's, going and stuffing them all into one texture packed together so that when we want to go draw these things, we can simply sample each of those little letters and get a nice clean mesh. Flip this again. It's a quirk of OpenGL is that the output textures actually are upside down and then sort of flipped when they're presented onto the screen. So when you're looking at textures, they're usually organized right side up in the way that you hope that they would be. But on output, we have to kind of remember to toggle back and forth between these views to get it where we need it to be. But anyway, so this is not a great example. Actually, let's boot up something else so we can look at a more complicated example. Like if we go and launch, let's launch a different application. Kaiju Defense Club has a lot of text in it. So let's just launch that. Take a trace. We can get a better example. So let's go in here. We'll take a screenshot. I'll do one of these traces. Let's go find some place in this render pass where it's rendering a bunch of text to the screen. This draw here should have, yeah, here's an atlas. it's actually still pretty small, but you can see a little bit more what's going on here, right? So as we needed to build strings using the fonts used by Kaiju Defense Club, it is basically rendering the glyphs for those fonts into this big texture, and then is just taking little pieces of this to build the actual stuff that goes on the screen. But what this means actually is that, like, if you noticed, there's a bunch of stuff that's getting rendered to the screen at the same time on this draw call, right? So like before this, there's no text on the screen. After this, the lobby and the missions and the borders and all that kind of stuff. That's because these are all packed into a single draw call. And this is using essentially that technique, right? Like there's one draw call that's getting sent that has a bunch of mesh geometry in it, and each of these little squares sampling a different part of that larger Atlas texture. This is a really solid optimization across the board. It's more memory efficient. It's fewer draw calls, which are expensive on some platforms like the web. And it's just overall a good enhancement. So let's steal the code from the GUI module that does the Atlas and start building an Atlas for all of our card textures. Okay, I'm going to close this down, get back into Vapor Solitaire. So our GUI module is here. Actually, that's the experiment module. Come in here, go to the Atlas. And I think what I'm going to do for now is just copy paste this into a new module. Let's go make a new module here. Call it Atlas. And modules need an init script. This one's going to be really simple. It's just going to return. Let's do this. I'll just return this whole class. And you'll see a little bit of the logic that is contained in here. Oh, actually, so I take it back. We are going to have to modify this a little bit. So this is working with font glyphs specifically, and we're going to want a slightly more generic system. I'll leave this copy pasted in here because we'll want to follow roughly the same routine, but we're going to want to do this in a more generic way, so it's not as it doesn't have as many tight assumptions about textures. But the other thing that I want to do here is go ahead and make a tests folder. Let's just call it texture pack. We'll give it its own init script. And it's going to need a manifest as well. So let's do that. Just to explain something about how our system works is any individual application in the Tweaks engine can be just a simple test script. Actually, I'll show you. We can come over into the Twins, or no, sorry, not the Twins folder. Let's open up the Tweaks tests specifically. Go ahead and save that file. So we write a lot of unit tests for the core engine to show, like, there's a bunch of these in here. Let's run some random ones. Let's look at fonts display. So we can run this one. So you can see Tweaks program, like app, can be as simple as like a single file with just like a little bit of code. This one is doing some work to test the font module, and so it's getting information about code points and then drawing these screens to quads to the screen. It's not hyper efficient, but it's a great little simple test, and it's really easy to kind of bootstrap things and get going with like displaying a simple texture. So we're going to follow this pattern and create a test specifically for our new Atlas module, so we can start looking at whether it's working or not. To show you maybe a more complex example, here is GLTF Draw. We use GLTF for 3D model format. It's a great open source standard that has nice physically based textures. I think I'll have all of the like GLTF sample models loaded in here, so you can see this test was great for us for basically making sure that we supported all of the kind of core features that we needed for GLTF in order to include the models in our games. So But we're going to start simple. Let's look for maybe like the simplest texture rendering thing that we could do. Let's see, what is this one doing? This one's literally just a blank screen. Slightly less simple than that, probably. Qmap display is probably too big. Here we go. Here's good. Here's like 5 lines of code. Loads a nice, pretty 2 weeks image. Let's go back to our Vapor Solitaire project. And we'll just paste this for now. Let's disable this code to load the logo. Yeah, so that program should run. Oh, right. Okay. I have a launch configuration set up here that always just runs Vapor Solitaire no matter where you are in this project. So let's add one for this test. Just copy paste this guy. Call it launch Atlas texture pack, and then we'll have it run it from inside of that folder. So this would be Atlas test texture pack. We don't need that argument there. Oh, I didn't actually switch the launch parameter. Let's come over here. Okay, let's take a look at why that didn't work. Oh, I think this is maybe, oh yeah, this path is wrong. Do modules. There we go. Oh, did I still not switch it? Still didn't switch it. Oh, interesting, okay. Tried to load the manifest. Live streaming coding is challenged because you're going to see all the sort of normal workflow things that I fall into, and then I'm bad at multitasking, so vocalizing what I'm doing as I'm doing it is going to be tricky as we run into little issues. But this manifest file is basically the thing that says what modules, extra modules this project needs. In this case, I think we can start with none. We got a little bit further. Okay, cool. That's a good example of our debugger. So error has occurred. It's because I commented out this logo thing, so when I have a texture in here, the thing that it's failing to load, or it's, this is crashing because it's trying to draw a screen quad that doesn't have a valid texture because we're passing null in. Got a nice little error that makes that clear. So let's put a logo in there. Let's go copy that logo.ping that this test uses. Actually, I know the next issue we're going to run into, which is the load's not going to fail because we didn't specify that we need that image. But just to walk through all the steps, let's go paste that image in here. Nice 2 weeks logo. Let's uncomment this line, and then it's going to crash on images because we didn't say that that was a module dependency for us. So let's go over the manifest. Let's say that it is a module dependency for us. All right. Okay, so we copied the test. It's running inside of our project here. The other thing that we want to do, though, is take a dependency on this Atlas module. So let's do that. This @ prefix means that we want to load a local module instead of one of the built-in ones in the engine. Show you an example, more complex manifest. You can see these here. Since this is a test, though, like if we go and look at some of these other tests that we have written in here, you'll notice that these also include this kind of local module path parameter here. This will tell it where to look for the local modules relative to this project. So we're in texture pack, so we want to pop up 3 directories, exactly the same as the thing I copy-pasted. That'll let it access the Atlas thing. So we should be able to run it. That's looking good. You can come over here. I'm just going to local atlas equals atlas.new. Let's just verify that we have access to. Yep, we loaded this function. It's a Lua module, so it's just a table with a bunch of functions that are contained inside of it. And we can see, yep, that's all the code that we copy-pasted into this module over here. Okay, so let's start modifying this. so that it can work for generic textures. So let's look at this. I don't think we need this glyph buffer type. Right, this existed to, I believe, yeah, this is the surface that is getting used for the texture. So this is like the raw image data that it's rendering the glyphs into. We don't need that, at least not in the same way, I don't think. So let's simplify this a little bit. Well, actually, let me think about this for a second. So what we want to do is create a buffer that's going to contain all of the image data, where the way that that generally works is that you build that in memory on the CPU side, and then you copy that into a GPU texture. So we probably are going to want a buffer. In our case, we're not going to want an 8-bit buffer. We're going to want a 32-bit buffer so that we can store arbitrary texture data. So let's go ahead and change this to texture buffer type. Still not totally sure if we're going to need this or not, but we will keep it for now. Let's call it color, since that's what the buffer would be composed of. It's a bunch of 32-bit color values. This texture node code, I'm pretty confident we can keep as is. This is basically an implementation in Lua of that algorithm that I was showing from BlackPawn earlier. And it's doing the sort of recursive subdivision of the space inside of the texture to make room for all of the stuff that's contained inside of it. I think this default texture size is fine. Let's keep scrolling and see where we're at. Oh, by the way, I'm getting lots of these little yellow notifications because we use a relatively popular and common Lua extension that provides a language server, and it's got a bunch of smart forward declaration stuff, but we haven't actually done the work to make it totally understand how our class types work. And so if we want to make it a little less noisy, we can just force it to understand that Atlas is a class type. That should make some of these go away. Possibly not all of them. I will need to do it here too because it's a different class. Okay, it's getting closer. All right, so it doesn't know what child A is. That's fine. Not worried about that. This is fewer yellow squigglies than we had before, so we'll keep going. But yeah, so all this code looks fine. This init function seems fine. This was written to have support for textures and single channel textures. Let's just have it support a single array of textures for now. And then this is where we're going to start wanting to change things. So instead of allocating a glyph, let's allocate an image. And then instead of passing font and code point information, let's just pass the size that we want. So size X and size Y. This is doing a bunch of math to figure out. Oh, actually, okay. So what this is doing here, this is the code to allocate a chunk of that larger texture buffer. This was written for the single channel use case, which is what's used by the font system. But I think actually what we want here is code that's just allocating space for an image. We want to keep this constraint that you can only allocate images that fit within a single texture. So the way that this works is that the Atlas is trying to pack everything into textures, but eventually if you allocate more stuff than will fit in a single texture, the system is capable of like creating multiple textures and keeping going. But it does have sort of like a predefined size for what the Atlas texture is. And 2048 is a good upper bound for compatibility with most devices. There's some mobile devices get grumpy if you try and allocate more than a 2K texture. So that's the limit. That's the envelope that we try and operate under. But yeah, it's correct for it to check to make sure that you're not trying to allocate a texture bigger than that, because that's not going to work. And then these single channel node things do not feel like something that we need. This is running through. Okay, so we do need. I think I killed an array earlier that we need. So we'll do texture nodes. We'll change this to texture nodes. And so what this is doing is calling this, and it's using this class up here, which is allocating space inside of this tree view. Actually, if I still have that website up, let me go back to Black Pond's page. I can show you what this looks like again. So this is essentially this code, and what it is doing is when you go to allocate a texture, it's looking at this tree and figuring out where it can insert it, and then updating the nodes so that it has the record of the insertion happening, and it's building a nice packed tree. So what we're doing in here is for every texture node that already exists, we're trying to insert it, this new size that we want allocated. Returning it if it fits into one of the existing nodes, and if it doesn't, that means that we don't have any textures that have space for this image, and so we need to create a new texture. And create a new node associated with it. And we're going to store the texture in here, and then we're going to store the new node for it inside of this texture nodes array. And then we're going to insert this new space. And we know that this will work because it's a brand new texture. We've already checked to make sure that we're not looking for a size bigger than the brand new texture that we created. So the insert's guaranteed to succeed. And then we will return the texture that we are inserting it into, as well as the position inside of that texture where it got inserted. So this actually does not look correct. This may be a bug in the other code too, actually. But what we want to return is the node, or is the texture itself. Actually, it's interesting. So this is returning the texture index, and this is returning the node itself. So this is returning, this actually could be simplified to just say root. But these are returning two different things, which does not look correct. Let's think through what we want. For now, let's return the texture index in both places, and if that winds up not being the right thing, we will revise. But I just want it to be consistent as a starting point. Okay, so let's go and create a new atlas. We actually, to do this correctly, we need to pass in the display. And then let's think through exactly how we want to, I think what I want to do for this test is basically just take that logo and pack it a few times and then output the result. So let's do that. Instead of actually having loaded this logo as a texture, let's instead just load it as image data. And just for the sake of kind of showing this incrementally, we'll start here so you can see what gets returned by this images.decode function. So what actually what it does is it loads that PNG file, and what it's returning is the dimensions of that texture, size X, size Y. This is the number of color channels. This is the packed data. And actually, I don't remember what this third parameter is. We can actually probably use... Do we not have... Generally, we have pretty good autocomplete on the documentation here, but it doesn't seem like we do in this case. Well, in that case, I'll just show you how this code looks like on the native side of the engine. So our base engine is just written in native C. And this, the module that we use for loading images uses Sean Barrett's STB library, which is a really great single header open source library. But, oh yeah, okay. The reason I don't have documentation here is because I didn't document this function. We can just figure this out here. So the values that it's returning the X dimension, it's returning the Y dimension, it's returning the number of components in the image, which should be 4, because it's a texture with alpha. The texture memory itself, like basically image buffer, and then I guess what it is passing here is the size of each of the individual channels, which is useful for when creating the graphics textures, but it's not a detail that we necessarily care about. But let's unpack these. So let's do size X, size Y, channels, data, channel size. Okay. Just verify that that all looks good. Oh, and equals would help. Did not all look good. Size X, size Y, channel, data, channel size. Right, that looks good. All right, and so now what we're going to do is create an atlas, and the thing that we want to do is pack that image data into the atlas a few times. So we can do atlas, let's call it pack image, and let's pass it size X, size Y, data. And let's just operate under the assumption right now. We probably are going to want to modify this so that this takes the number of channels and maybe the channel size and uses that to create it. Let's just go ahead and do it. Let's just go ahead and do it the right way. So let's go back to Atlas. Let's take, so we take display, and then we're also going to pass the number of channels. And then I'm going to use a kind of Lua convention here to set some defaults. So in Lua, if you use the OR operator, then if the first value is truthy, basically meaning it's not false or nil, then it'll return that value, as opposed to like other languages where if you use a Boolean qualifier like this, it may return true or false. But this gives you sort of like, kind of like a question mark operator that's popular in more modern languages. Because if this is falsy because it's nil or false, then it'll return the other parameter, which is a 4. So what this is saying is basically like, hey, if somebody passed this parameter in, then use it. Otherwise, assume that the number of channels is 4. Same thing for channel size. Take it if it's provided. If it's not, let's just assume that it's 1. And then we're adding a function called packImage here, which is going to specifically pack the image here a few times. And then we're going to want to display, clear the display, and then we're going to want to draw the I'm just going to go ahead and make this default display square. We'll see if that winds up being a problem down the road. Oh, right. Actually, so we're going to want to return the texture itself. We figured out the thing that we wanted to return here. But let's do this. And now we'll return the texture from both of these code paths. And we can come in here and modify those parameters that we stored earlier. So we've got channel size here. Oh, actually, I just noticed there's a nice little message from somebody in the chat. I was asking, will this be available on YouTube afterwards? Probably. I'm not sure if the content is going to be particularly high quality. This is just an experiment, but if it doesn't go too badly, I'm happy to just have it on the channel so that people can review it later. I don't know how interesting these are. This is just me showing my work and talking through it as we do it. But if it's interesting to people, then I'm happy to leave it on the channel. We'll see. But yeah, so anyway, back to this. What we were doing here is we're now storing more information about like this 4 in here is the number of channels that are associated with this. We can just go ahead and actually pass the configured value now. And then this, if we have a 3-color channel, then this class will work for it. If we have a 4-color channel, which is usually what it is, this will work as well. It looks like this texture image field index is no longer being used, so we can just delete that. Okay. All right, and this is okay. This is kind of nice. So what's going on here is that this function is returning the positions inside of the texture. This is the old function that was from the class that we copied that is designed for packing glyphs. Let's write a new one. We call it pack image. So we're going to do function atlas pack image. And yeah, it takes a size x, a size y, and a data. And then we're going to allocate the image, and then what we will need to do is actually store the image data, but what we want to return is the UVs. So we're going to copy paste this code from down here, because the UVs are normalized coordinates, right? So this texture is 2048 by 2048. We're getting the positions back in the absolute coordinates inside of that buffer, but what you want to send to the graphics card is here are the relative coordinates inside of it. So we just need to kind of compute what those coordinates are as a result, and then we will return the texture and the UVs. So if we come back over here, we're only going to grab the texture parameter, and we're going to assume that all of these things pack successfully into a single texture. Just for purposes of this test, and then we're going to draw that texture to the screen. We don't care about the UVs in this case because we just want to show the whole texture. But let's basically fill it up. And then I'm just going to, for the sake of verifying, let's go look at the graphics module. And look at that draw screen quad function. Oh, actually, this is a good example. We can look at this in the raw code, but we actually did do the work to provide good documentation here. So if we look at draw screen quad, you can just see what the parameters are here. So the first parameter is texture or program that we want to render, and so we want to pass it our texture. And then the starting position of the quad and the x dimension, these are in screen coordinates. So this is, we do want the defaults, but 0, 0. And then the ending position defaults are current viewport x dimension, so basically it's going to fit it to the actual screen dimensions. So those defaults are good. So all we need to do is draw the screen quad, and it's going to stretch correctly across the display. So we actually theoretically could run this function now. I'm going to leave that there for a second just so we can have it as reference. And let's just step into it and see if it's working in a way that we expect. So we're calling that alloc image function. Did it create a texture? It did. Get some reasonable positions out of it. Let's look at our locals. Yeah, that's as expected. Okay, so that allocated the space correctly. We're going to go pack that same image again. Let's see how it did it. Okay, yeah, so it shifted it a little bit to the side, but both of those got packed. The texture is going to be all black because we haven't actually done anything, but we did fill up this atlas. And then if you're just curious to see more of the data structure, now that it's packed a few things, we can come in and look at our texture nodes. We only have one because we only have one texture. And what you're seeing here is this child tree, right? And so this outermost node takes up the whole space, but has a couple of children. If we dig down into the leaves, we'll eventually get to an individual texture, which this is that first one. This is the second one. It looks like this one has multiple children as well. So that got split in a different dimension. Anyway, so tree structure containing the positions of all of these textures inside the space. So we've like allocated stuff successfully. Of course, it won't look like anything because we haven't actually put any image data in there. We're just clearing the screen to white and then rendering an empty texture on top of it. But so the next step is to actually update that texture. So if we go back here, let's take a look at this texture update function and see if it has all of the fields that we need. Okay. So this doesn't actually document all the parameters here, but looking at this, yeah, it does look like you can pass an image buffer and update a subset of the texture, which verifies actually earlier I thought that we were going to need this buffer type. We don't, because we don't need to directly fill the backing data for it. We can just use this update texture function to update subsections of the texture. So it looks like all we need to do is come in here, update this data, and then we're going to pass it. Looks like we can pass it sides and then strides. So we have x1, y1, and then our stride is going to be the actual total texture size here. If you're not familiar, stride in a texture is the length of a row. So when you're copying stuff into a subsection, you're going to copy a line of pixels that's in the sort of like smaller space that you're trying to allocate, and then you're going to step the whole stride to the next row, copy the next section of pixels and that kind of thing. So the stride is the size of the outer texture, even though the distance that we're filling is from only a smaller dimension inside of it. But that theoretically should be correct. So let's run it and see what we get. We get a crash, so it is not correct. Let's take a look at it. So we're passing it a buffer, passing it the dimensions that we want to store it in, and then we're passing the stride. Do we actually, it's interesting. Okay, so I think I'm reading this wrong. Of course, the texture already knows its own stride, so it doesn't need that information to copy it correctly. It needs to know the stride of the information that is being provided, which we can make an optional parameter here and then do the same thing where if it's not provided, we compute a good value for it. So the default stride that we're going to want is going to be the size of the texture. And we can actually simplify this to stride or size x. Let's try that. And look at that. We have a packed texture. We could go pack it a few more times if we wanted, just for the sake of testing it further. We got a bunch in there. This is probably full. Probably can't pack another one in. How many did we actually paste? We did 1, 2, 3, 4, 5, 6, 7, 8. Let's see. If we do a bunch more, it's going to create an extra texture. It'll probably look the same. Yep. Because this, if we go, let's go look at what this last texture that we loaded is. Set a breakpoint here. Rerun this. And then we can see, yeah, these are different pointers. So, yeah, but anyway, we have successfully packed an image. So now we have a generic texture packer. What we want to go do now is go stick a bunch of cards in it. So let's go do that. Our cards module just to show how this works. The 3D object is called a canvas card. But when a card gets created to be rendered, it uses the same model that is shared across all of them. It's a GLTF file in here. I can actually probably the easiest place to show this would be in Blender. Oh, right. So I'm looking in the wrong place because it's actually in the module. Oh, and right. I can't just open it as a blend file. I need to import GLTF. Ah, yes, it's tiny. There we go. There's our card. Let's turn on rendering for it. There we go. And actually, this is a fun way to demonstrate actually some excessive details that we put in here. So I'm actually using the clear coat extension inside of GLTF and have this little nice like lacquered texture that you get on real cards. So it looks nice in 3D. The little placeholder card back there. But yeah, anyway, so it's a 3D model, and what this code is doing is coming in here and creating that model and then swapping the textures that are assigned to it so that it can get different backs and fronts. So what we want to do, and specifically actually for the cards, to save some memory, what we do is we have a bunch of .svg files for all of the individual cards. Let's see if actually those are... So yeah, you can see a bunch of SVGs, which have sort of like nice vector representations of all of the cards. And then we render those SVGs to a texture, and then we override that SVG material. And so you can see this is doing the thing where it's creating a material from the card front. So what we want to do instead is have an atlas that is storing all of the cards, and then when it's going to replace the material, it renders the SVG into the atlas, and then sticks that subset of the atlas into the material that gets associated with the card. So let's go look at that function, see if it's apparent how best to modify it so that it can work on an atlas. So here's the thing that's doing this. It is rasterizing an SVG texture. This is currently just creating an individual texture and returning it. And so what we want to do instead is probably have this rasterize the texture into an atlas. So let's take a texture atlas and look at how we want to modify this. So it has a texture cache already. Okay, actually, I don't think we want to pass in an atlas. I think we want this to create atlases as it needs. So let's do this. It already has a display cache. Instead of having a texture cache, let's just have an SVG atlas. Just want to verify this is the only place where this is used, okay? Okay, and I don't think we added atlas as a dependency of the cards module, but let's go ahead and do that. Okay. We do still want to cache texture information, though, keyed on the SVG data. But what we want it to be is the reference to the Atlas texture plus the UVs that correspond to it. So instead of actually just deleting the texture cache, let's change it to store that information. So instead of just storing cache texture, let's call it Atlas texture. I see Foggy in the chat. It's good to see you. I'm just reasoning about what this code is currently doing because it's doing some tricky stuff. This is metatables in Lua are ways that you can tell the underlying Lua engine that you want some more complex behavior than the default. And in this case, the more complex behavior it's asking for is to hold weak references to both the keys and values in this texture cache data. I think we don't want that because if we lose, in this case anymore, because we're packing all this stuff into an atlas, if we lose references to the layout of that atlas, it's going to be leaked information because it's not going to simultaneously get cleared up from the atlas. So eventually we'll probably want to change the Atlas module so that it has the ability to not only allocate, pack stuff into it, but also unpack stuff so you can free memory and use it for other things. We don't need that at the moment, so I'm going to avoid that problem. But I'm just going to go ahead and delete this. And then what we actually want the Atlas texture info to be is a table that has all of the packed information. So what we want here, I believe, is to do this. Oh. Autocomplete's guessing wrong in this case. What we want to do is do display cache .svg atlas pack. Well, pack SVG actually might be nice. We can think about whether or not we want to implement that or not. But what we want to do is pack an image. This is more, I'm realizing now this is more complicated because this is designed so that you can pack multiple, or you can cache. This is a two-stage cache. So the outer stage of the cache is for this SVG. Do we have any cache an array of textures, and then inside of that, for a specific size and scale, pack that texture in. So let's back up a step. I should have read this function more carefully before I dove in to start modifying it. Okay, so what do we want? We want, for a particular SVG, no, we still want everything packed into a single atlas. So we do want an SVG atlas in the cache. New atlas, new display. The defaults are fine. And then I think we do want to, so this same texture cache here, we want to come from the SVG data. Still suspicious about this having weak references for its keys and values, but I'm not going to preemptively delete that until I've thought about it more deeply. And then it's creating a key based on the specific size that it wants to use to generate the SVG at. I think that's good, and then we want to keep it. And this is the thing that's currently storing a texture, but instead we needed to store texture data that includes the position inside of the texture where it's being used. So let's do this. Let's call this texture data. And then right now it is rasterizing an image here. Okay, great. This will be straightforward, I think. So what we want to do in this case is take our display cache, which now has an SVG atlas, and then we want to pack the rasterized image as so. This is going to return texture U0, B0, U1, B1. And then what we are going to want to store here as texture data actually, just as a Lua shorthand, we can do this. This will automatically store all of these fields as an array here. We can then do this. And then we can do table.unpack to return all of those things. Okay, I think this is correct. We will set a breakpoint though, so that the first time we actually try and run it, we'll step through it and see if it looks good. This is now returning additional parameters, so let's do that. And then we're going to want to pass those into this function. So it looks like this already takes a third parameter. Let's see what it takes. It takes node, takes blend modes. Okay, so we're going to add parameters at the end of this. Handle defaults in this case here, but then we want to explicitly pass false for blend mode on the SVG material, and then pass through the UVs. See if autocomplete guesses this correctly. It does. All right, and we need to also capture these return values here. Okay, now let's go look at how we override the GLTF material so we can get those UVs in the right spot. Okay, so it is going to come through, and so this is that GLB that we were looking at earlier. It's finding the material that is the card front face, and then it's cloning that material and then overriding some of its parameters in order to apply it. So this won't look correct yet, but let's just leave it as is without changes. What we should see is this stuff start populating in a texture atlas, and probably a card. Well, no, the texture atlas UVs are going to be weird, so it's going to look strange, but we can. This should be runnable. If we switch back to Vapor Solitaire, we should hit our breakpoint. And let's just step through this and make sure that this is doing something sensible. So we are going to render an SVG. It's a small image. So we're going to come in here and create this texture cache. We won't have texture data, so we're going to create a rasterizer. We're going to rasterize that image into a texture. We're going to pack it into our atlas. It's got the texture, the UVs, sticking that in the texture cache. So the next time something comes through, it's going to get returned that same texture in UVs. And then we are going to receive that texture data. Okay. So we should be able to just run now. If we hit play, our cards probably look pretty weird. Okay, cool. Actually, this is a really interesting result, right? This is actually an interesting way to see the work that we did, because we're just mapping the atlas. We haven't done the work yet to only show the subset of the atlas that corresponds to the specific card that we're at. But it looks like we were able to pack all of the cards into 2 atlases, because it looks like these are all the same, and then we've got another one in here. We can verify that if we go back to RenderDoc. Let's load up our settings again. Still pointing at Kaiju Defense Club. Let's go back to Vapor Solitaire. Let's run it. Let's take a capture. Oh, too early because I haven't displayed any cards yet. Let's take a capture. And still the same number of draw calls because doing a bunch of stuff, but here's one that's rendering some texture, so let's look at the inputs. Yep, there's our atlas, all packed in. Okay, cool. This is looking solid. Let me zoom in. And so the cool thing about this is like, once we get this optimized, oh, actually, so here's a little bit of magic. You'll notice that instead of drawing 52 draw calls now, the screen is only, there are only, looks like 10 or so calls that are happening here. And that's because the underlying 3D scene manager that we did already looks to see if materials are shared across all of these elements. And if it's using the same textures, then it bundles them into a single draw call. So now we're rendering 52 card backs at the same time. And then I got to figure out what this is. This is like a placeholder texture that's in that model, but this feels like an unnecessary draw call that we can optimize out. But we're already getting to the point where we are just drawing, it looks like 44 of the cards in one pass, which is probably how many textures we can pack into one, and then the other cards in a single pass. So we went from 100 draw calls to 10. So this should be a really substantial speed up for us in efficiency once we get it looking right. It's not playable in its current state. Okay, but that's very promising. Okay, let's go ahead and close out this again. Get back to this. So now we need to get the UVs in the right spot. The way that we need to do that is that we need to further modify this material so that it's accounting for the UV positions. And I actually don't remember offhand exactly how this works in our sort of GLTF material stuff, so we're going to have to do some code spelunking to figure out what we want to modify. But let's do that. Let's go into the GLTF module is a built-in one, so it's over in our Visual Studio 2022 project and not VS Code. But we can still see what's going on here. And let's go look at... Okay, well, I can talk through this in steps. So this is the global shader that we use for rendering GLTF models. And it's using this texture sample source helper function. This code is a little confusing because we're doing some macro magic to compose all of this. But essentially, it is using the vertex texture coordinates to sample if there's no UV transform present. So I think what we are going to want to do is assign a UV transform to these things, which will take the normal texture coordinates, which will stretch over the whole card surface, and then shift them so that it only applies to the subset that we want to have visible. So let's take a look at what we need to do in order to get that to be applied. Okay, so we've already cloned this material, and so it looks like what we can do is set this base color UV transform property to true. And then it is using a 3x3 matrix to transform that. So let's go ahead and do that. And we'll just pass it an identity matrix for now and make sure we didn't break anything any worse than we already have. So we want to do override uniform buffer. Set uniform, and this one is going to be called has base color UV transform, and set that to true. And then for now, I'm just going to set the base color UV transform to an identity matrix. Probably not the cleanest way to do this, but this is where we're going to start, just to make sure that this works. Autocomplete's doing a good job today. So we'll do like that. And this should look the same. It is expecting a 3x3 matrix, and I got a number. Oh, okay, well maybe we do actually have to pack the matrix. Let's see. Just reminding myself. Oh, okay, this is easier. We can just do this. So we have a mat3 library. Instead of typing it out like this, we could just do mat3 identity. Okay. As expected, looks the same. Okay. Just reminding myself what our mat3 library doesn't have much of anything. I think it is mostly used internally. So we'll probably need to expose some things. But what we want to do with the matrix basically is scale it down. So like we're going to assume that we have a texture that's mapped from 0, 0 to 1, 1, corner to corner. And we want to transform that so that it corresponds to the UVs. So we need to offset it by its initial UV position, which is U naught and V naught. And then we want to scale the uniforms so that they match with the specific dimension of the subset of the atlas texture that we're asking for. And so with a 3x3 matrix, the thing that we want, actually, you know what? Saying this, probably the thing that we should do is write a helper function that lets you compose a 3x3 matrix that with a transform and scale. That would probably be the easiest thing. But I'm debating whether or not I want to write that or just kind of hack through this at the moment. I don't think I want to write that right now. Actually, I'm going to check a different thing first. If we go to graphics module, let's look at that mat3 error, because I was surprised that I couldn't just pass 9 floating point numbers to it. Yeah, this is written as if you should be able to pass numbers in. So let's go back to figuring out why that didn't work. Let's replace this with 9 floats again. Doesn't need that last. Let's see what error we get. This is the set uniform function. So we should be getting here. I'm going to debug this on the native side. Configure the debugger to run Vapor Solitaire. Uh-oh. Why do we have build errors? That shouldn't be the case. Oh. Can't build because there was a process running. So this should be fine. Okay, it's crashing earlier than that. So let's see what's tripping it up. Don't understand. Oh, well, right, because we're hitting whatever other call is getting is going to sampler uniform here. So something other than geomat 3, presumably. Okay, I'm going to do something more complicated so that it's easier to debug this. Oh, hold on. I'm going to tell it to open up a debug connection so we can attach to it with both debuggers. And then we are going to run this like this. Get to this point. Oh wait, hold on, sorry. Confusing myself. Okay, so it's attached in the native debugger now. And then we are going to attach to it with our custom Lua debugger. We're going to set a breakpoint just before we get into this call, which means that we'll have skipped everything that was hitting this function before we got here, and then we'll just step over this. Oh, interesting. Okay. Aha, okay. I think I understand why this is. This is a graphics uniform buffer. It is not a graphics program, so I am just looking in the wrong spot. Here we go. All right, okay. I'm going to show you what we're going to do. This doesn't have all of the, this function that we're calling doesn't have all of the nice type conversion stuff that I was expecting to be there, which it probably should, but we're going to skip that for now. We're going to add a function in here called pack. This is going to let us make a matrix type by passing it a bunch of numbers, and then we can just we can pass the compose matrix to this function. So just a point of comparison, let's look at like vec4. We'll have a pack function. We can probably just copy paste it and modify it. Nice and simple. Okay, and I'm just going to word replace this because I think this is going to mostly work if we fix a few numbers. And actually, let's look at mat4 and see if it has one. Because if it does, it's going to be closer to correct. It does have a pack function. This wasn't even the right name. Oh, this is cute. It was using vector functions that we were missing. Okay, well, we will be cute in the same way. Change some 4s to 3s. Let's see if that builds. Does not. Missed something. Ah, I missed. Change it a 4 to a 3. All right. That function might work. Let's try it. Heap corruption detected. It did not work. Let's figure out what's going on here. Okay, I'm going to leave this alone for now. We're going to look at... Oh, yep. That's some heap corruption. Some more 4s that needed to be 3s. Let's try this again. It was basically copy pasting past the end of the buffer. Set a breakpoint here. See if that packed into a coherent thing. Looks like a matrix. And we should get the same result of just seeing the whole atlas. Yep, that is expected. Okay. But now what we can do is stuff the UVs in the right spot. Actually, hold on. I'm going to do... Let's do this. We made these parameters optional, so we need to set defaults if they're not specified. Autocomplete's doing a good job. And then we want to transform this. So and we want to compute the size that we need to scale by, and this scale needs to be 1 over du. Actually, let me think about this. No, I think actually we just want du dv here. Let's see what this does. Not looking promising yet. Let's set a breakpoint and see what our transforms wind up looking like in here. This is hopefully one where we didn't specify UVs. Let's come down here where we know that we're stuffing stuff into an atlas. That's not getting called. Oh, okay, that's right, because it's the card fronts that have the cards on them. So set a breakpoint here. Do we get coherent UVs? Yep, we do. Okay. Let's come down into here. Do these values look like reasonable things? They do. Get a transform in here. What does this transform look like? Looking like a matrix. Ah, I think I see the issue. Okay. So yet to be seen whether or not we've done the math exactly right on this transform or not. But this is caching override textures purely based on the material, or based on the override texture that we're providing, which is now an atlas. So every card is going to get the same material override because it's not composing a key that accounts for the UV coordinates that are present here. So we need to think about how we want to do this more carefully. This is also, I'm realizing now actually this is going to change the way that the instanced rendering is going to work because it's using the material keys to figure out which things it can instance. So probably what we can do is fix this, but we'll wind up with more draw calls and then we'll need to modify some other state to get it to be more optimized. But if we can get to the point where we're packing all this stuff into a texture atlas and then rendering the cards correctly, I'm going to call that good for now, and then work on the follow-on module changes so that we can take advantage of that to get it back down to fast draw calls. But let's do this for now, which is probably just not cache and always override with the new material. And a hacky way we can do that is commenting out this line, because then it won't show up in the cache, which means that it'll go load it for that texture later, it'll never find it, and so it'll clone new material every time. So let's do that and see what we get. Breakpoint that we set earlier. Okay, still not getting the result that we were looking for. Let's go into RenderDoc again, see where we're at now. We should see a bunch of draw calls again because each of these cards should be getting individually rendered. Yep, a bunch of draw calls again. Okay, let's go find, here's one that's got an individual card. Getting past that whole texture sheet. You can see some of the other textures that are getting passed through for the lighting and things. Let's go look specifically at the pipeline state because we want to look at the vertex shader. Actually, I guess we probably, this is, I don't know if it's doing the UV transforms in the vertex shader or not. Oh, you know what? Actually, an issue that we may be running into. Let's take a look at the GLTF module again. Because I think UV transforms may be an extension that we have to turn on if they're not in use. Yeah, KHR texture transform. Okay. So we're setting variables that are not used. I'm surprised it actually doesn't crash. I'm surprised that those booleans are getting passed through. Let's look at what we need to do to turn on this extension. Well, hold on. Let's just keep looking a little bit further here and see what other variables we have in here. So this is the value that I would have expected to be true. It is not. And it has an empty transform parameter. So actually, maybe it doesn't have to do with the extension. We may be able to fix this by just looking directly at the code and figuring out why these aren't getting set. Okay, let's go look over here and see if there's anything apparent. Oh, well, actually, probably this is not happening. There's a commit step. So the uniform buffers get composed in memory and then copied over to the graphics card. So like we were updating the memory, but I don't think we were actually committing it and causing it to, well, let's yeah, okay. Let's always commit the uniform buffer at the end. Hooray! Look at that. We got card backs displayed the right way. Okay. I think this is... Oh, actually, I just got a disconnect notice. Am I back? I'm back. All right. I think I may have lost connection, so just for the victory lap here, let's launch again. All of the cards are getting dealt in the right spot. They look good. Let's load it up in RenderDoc. Load the last settings again. Deal out some cards. Let's take a frame capture. Let's put that ace in the right spot. Okay. So it's still a bunch of draw calls, but looks like that ace is actually drawn real early. So let's look at that ace. It's pulling from this texture sheet. It's updating its UVs the right way. It's looking good. So the very last step is just going to be basically binning all of the draw calls for the cards that are using the same texture sheet into a single draw call so we can get back to that nice tight list of 10, and then I'm going to start doing some performance profiling. But I think this is a good place to stop because we fully implemented a new feature, and then opens up some new optimizations that are probably going to be a bunch of boring debugging on my part. So I think this is a nice, tidy place to clean up the stream. Thanks for watching, everybody. It's nice to see you all here.